shift effect and determined that this segment of 45-year-old males living in the Northeast is predictive with respect to churn rate. After translating this into a SQL query, a query tool could then be used to find the matching records in the database. Query tools generally have the ability to execute sophisticated logic, including computing summary statistics over subpopulations, sorting, joining together multiple tables with related data, and more. Data scientists often become quite adept at writing queries to extract the data they need. Online Analytical Processing, OLAP, provides an easy-to-use GUI to query large data collections for the purpose of facilitating data exploration. The idea of online processing is that it is done in real time, so analysts and decision-makers can find answers to their queries quickly and efficiently. Unlike the ad hoc querying enabled by tools like SQL, for OLAP, the dimensions of analysis must be pre-programmed into the OLAP system. If we've foreseen that we would want to explore sales volume by region and time, we could have these three dimensions programmed into the system and drilled down into populations, often simply by clicking and dragging and manipulating dynamic charts. OLAP systems are designed to facilitate manual or visual exploration of the data by analysts. OLAP performs no modeling or automatic pattern finding. As an additional contrast, unlike with OLAP, data mining tools generally can incorporate new dimensions of analysis easily as part of the exploration. OLAP tools can be a useful complement to data mining tools for discovery from business data. Data warehousing. Data warehouses collect and coalesce data from across an enterprise, often from multiple transaction processing systems, each with its own database. Analytical systems can access data warehouses. Data warehousing may be seen as a facilitating technology of data mining. It is not always necessary, as most data mining does not access a data warehouse, but firms that decide to invest in data warehouses often can apply data mining more broadly and more deeply in the organization. For example, if a data warehouse integrates records from sales and billing as well as from human resources, it can be used to find characteristic patterns of effective salespeople. Regression analysis. Some of the same methods we discuss in this book are at the core of a different set of analytic methods, which often are collected under the rubric regression analysis, and are widely applied in the field of statistics and also in other fields founded on econometric analysis. This book will focus on different issues than usually encountered in a regression analysis book or class. Here, we are less interested in explaining a particular dataset as we are in extracting patterns that will generalize to other data, and for the purpose of improving some business process. Typically, this will involve estimating or predicting values for cases that are not in the analyzed dataset. So, as an example, in this book, we are less interested in digging into the reasons for churn, important as they may be, in a particular historical set of data, and more interested in predicting which customers who have not yet left would be the best to target to reduce future churn. Therefore, we will spend some time talking about testing patterns on new data to evaluate their generality, and about techniques for reducing the tendency to find patterns specific to a particular set of data, but that do not generalize to the population from which the data come. The topic of explanatory modeling versus predictive modeling can elicit deep-felt debate, which goes well beyond our focus. What is important is to realize that there is considerable overlap in the techniques used, but that the lessons learned from explanatory modeling do not all apply to predictive modeling. So, a listener with some background in regression analysis may encounter new and even seemingly contradictory lessons. Machine learning and data mining. The collection of methods for extracting predictive models from data, now known as machine learning methods, were developed in several fields contemporaneously, most notably machine learning, applied statistics, and pattern recognition. Machine learning, as a field of study, arose as a subfield of artificial intelligence, which was concerned with methods for improving the knowledge or performance of an intelligent agent over time in response to the agent's experience in the world. Such improvement often involves analyzing data from the environment and making predictions about unknown quantities. And over the years, this data analysis aspect of machine learning has come to play a very large role in the field. As machine learning methods were deployed broadly, the scientific disciplines of machine learning, applied statistics, and pattern recognition developed close ties, and the separation between the fields has blurred. The field of data mining, or KDD, knowledge discovery and data mining, started as an offshoot of machine learning, and they remain closely linked. Both fields are concerned with the analysis of data to find useful or informative patterns. Techniques and algorithms are shared between the two. Indeed, the areas are so closely related that researchers commonly participate in both communities and transition between them seamlessly. Nevertheless, it is worth pointing out some of the differences to give perspective. Speaking generally, because machine learning is concerned with many types of performance improvement, it includes subfields such as robotics and computer vision that are not part of KDD. It also is concerned with issues of agency and cognition. How will an intelligent agent use learned knowledge to reason and act in its environment, which are not concerns of data mining. Historically, KDD spun off from machine learning as a research field focused on concerns raised by examining real-world applications, and a decade and a half later, the KDD community remains more concerned with applications than machine learning is. As such, research focused on commercial applications and business issues of data analysis tends to gravitate toward the KDD community rather than to machine learning. KDD also tends to be more concerned with the entire process of data analytics, data preparation, model learning, evaluation, and so on. Answering business questions with these techniques. To demonstrate how these techniques apply to business analytics, consider a set of questions that may arise and the technologies that would be appropriate for answering them. These questions are all related, but each is subtly different. It is important to understand these differences in order to understand what technologies one needs to employ and what people may be necessary to consult. 1. Who are the most profitable customers? If profitable can be defined clearly based on existing data, this is a straightforward database query. A standard query tool could be used to retrieve a set of customer records from a database. The results could be stored by cumulative transaction amount or some other operational indicator of profitability. 2. Is there really a difference between the profitable customers and the average customer? This is a question about a conjecture or hypothesis. In this case, there is a difference in value to the company between the profitable customers and the average customer. And statistical hypothesis testing would be used to confirm or disconfirm it. Statistical analysis could also derive a profitability or confidence bound that the difference was real. Typically, the result would be like, the value of these profitable customers is significantly different from that of the average customer, with a less than 5% probability that this is due to random chance. 3. But who really are these customers? Can I characterize them? We often would like to do more than just list out the profitable customers. We would like to describe common characteristics of profitable customers. The characteristics of individual customers can be extracted from a database using techniques such as database querying, which also can be used to generate summary statistics. A deeper analysis should involve determining what characteristics differentiate profitable customers from unprofitable ones. This is the realm of data science, using data mining techniques for automated pattern finding, which we discuss in depth in the subsequent chapters. 4. Will some particular new customer be profitable? How much revenue should I expect this customer to generate? These questions could be addressed by data mining techniques that examine historical customer records and produce predictive models of profitability. Such techniques would generate models from historical data that could then be applied to new customers to generate predictions. Again, this is the subject of the following chapters. Note that this last pair of questions are subtly different data mining questions. The first, a classification question, may be phrased as a prediction of whether a given new customer will be profitable. Yes, no, or the probability thereof. The second may be phrased as a prediction of the value, numerical, that the customer will bring to the company. More on that as we proceed. Summary. Data mining is a craft. As with many crafts, there is a well-defined process that can help to increase the likelihood of a successful result. This process is a crucial conceptual tool for thinking about data science projects. We will refer back to the data mining process repeatedly throughout the book, showing how each fundamental concept fits in. In turn, understanding the fundamentals of data science substantially improves the chances of success as an enterprise invokes the data mining process. The various fields of study related to data science have developed a set of canonical task types, such as classification, regression, and clustering. Each task type serves a different purpose and has an associated set of solution techniques. A data scientist typically attacks a new project by decomposing it such that one or more of these canonical tasks is revealed, choosing a solution technique for each, then composing the solutions. Doing this expertly may take considerable experience and skill. A successful data mining project involves an intelligent compromise between what the data can do, that is, what they can predict and how well, and the project goals. For this reason, it is important to keep in mind how data mining results will be used, and use this to inform the data mining process itself. Data mining differs from, and is complementary to, important supporting technologies such as statistical hypothesis testing and database querying, which have their own books and classes. Though the boundaries between data mining and related techniques are not always sharp, it is important to know about other techniques' capabilities and strengths to know when they should be used. To a business manager, the data mining process is useful as a framework for analyzing a data mining project or proposal. The process provides a systematic organization, including a set of questions that can be asked about a project or a proposed project to help understand whether the project is well conceived or is fundamentally flawed. We will return to this after we have discussed in detail some more of the fundamental principles themselves, to which we turn now. Chapter 3. Introduction to Predictive Modeling. From Correlation to Supervised Segmentation. The fundamental concepts discussed in this chapter are identifying informative attributes and segmenting data by progressive attribute selection. The exemplary techniques are finding correlations, attribute variable selection, and tree induction. The previous chapters discussed models and modeling at a high level. This chapter delves into one of the main topics of data mining, predictive modeling. Following our example of data mining for churn prediction from the first section, we will begin by thinking of predictive modeling as supervised segmentation. How can we segment the population into groups that differ from each other with respect to some quantity of interest? In particular, how can we segment the population with respect to something that we would like to predict or estimate? The target of this prediction can be something we would like to avoid, such as which customers are likely to leave the company when their contracts expire, which accounts have been defrauded, which potential customers are likely not to pay off their account balances, known as write-offs, such as those who default on their phone bill or credit card balance, or which web pages contain objectionable content. The target might instead be cast in a positive light, such as which consumers are most likely to respond to an advertisement or special offer, or which web pages are most appropriate for a search query. In the process of discussing supervised segmentation, we introduce one of the fundamental ideas of data mining: finding or selecting important, informative variables, or attributes, of the entities described by the data. What exactly it means to be informative varies among applications, but generally, information is a quantity that reduces uncertainty about something. So, if an old pirate gives me information about where his treasure is hidden, that does not mean that I know for certain where it is. It only means that my uncertainty about where the treasure is hidden is reduced. The better the information, the more my uncertainty is reduced. Now, recall the notion of supervised data mining from the previous chapter. A key to supervised data mining is that we have some target quantity we would like to predict or to otherwise understand better. Often, this quantity is unknown or unknowable at the time we would like to make a business decision, such as whether a customer will churn soon after her contract expires, or which accounts have been defrauded. Having a target variable crystallizes our notion of finding information attributes. Is there one or more other variables that reduces our uncertainty about the value of the target? This also gives a common analytics application of the general notion of correlation discussed earlier. We would like to find knowable attributes that correlate with the target of interest, that reduce our uncertainty in it. Just finding these correlated variables may provide important insight into the business problem. Finding informative attributes also is useful to help us deal with increasingly larger databases and data systems. Datasets that are too large pose computational problems for analytic techniques, especially when the analyst does not have access to high-performance computers. One tried-and-true method for analyzing very large datasets is first to select a subset of the data to analyze. Selecting informative attributes provides an intelligent method for selecting an informative subset of the data. In addition, attribute selection prior to data-driven modeling can increase the accuracy of the modeling, for reasons we will discuss in Chapter 5. Finding informative attributes also is the basis for a widely used predictive modeling technique called tree induction, which we will introduce toward the end of this chapter as an application of this fundamental concept. Tree induction incorporates the idea of supervised segmentation in an elegant manner, repeatedly selecting informative attributes. By the end of this chapter, we will have achieved an understanding of the basic concepts of predictive modeling, the fundamental notion of finding informative attributes along with one particular illustrative technique for doing so, the notion of tree-structured models, and a basic understanding of the process for extracting tree-structured models from a dataset, performing supervised segmentation. Models, induction, and prediction. Generally speaking, a model is a simplified representation of reality created to serve a purpose. It is simplified based on some assumptions about what is and what is not important for the specific purpose, or sometimes based on constraints on information or tractability. For example, a map is a model of the physical world. It abstracts away a tremendous amount of information that the mapmaker deemed irrelevant for its purpose. It preserves and sometimes further simplifies the relevant information. For example, a road map keeps and highlights the roads, their basic topology, their relationships to places one would want to travel, and other relevant information. Various professions have well-known model types: an architectural blueprint, an engineering prototype, the Black-Scholes model of option pricing, and so on. Each of these abstracts away details that are not relevant to their main purpose and keeps those that are. In data science, a predictive model is a formula for estimating the unknown value of interest, the target. The formula could be mathematical, or it could be a logical statement such as a rule. Often it is a hybrid of the two. Given our division of supervised data mining into classification and regression, we will consider classification models and class probability estimation models and regression models. Note: in common usage, prediction means to forecast a future event. In data science, prediction more generally means to estimate an unknown value. This value could be something in the future, in common usage, true prediction, but it could also be something in the present or in the past. Indeed, since data mining usually deals with historical data, models very often are built and tested using events from the past. Predictive models for credit scoring estimate the likelihood that a potential customer will default or become a write-off. Predictive models for spam filtering estimate whether a given piece of email is spam. Predictive models for fraud detection judge whether an account has been defrauded. The key is that the model is intended to be used to estimate an unknown value. Predictive modeling contrasts with descriptive modeling, where the primary purpose of the model is not to estimate a value, but instead to gain insight into the underlying phenomenon or process. A descriptive model of churn behavior would tell us what customers who churn typically look like and would likely be used to work toward a causal understanding of the data-generating process. Why do people churn? A descriptive model must be judged in part on its intelligibility, and a less accurate model may be preferred if it is easier to understand. A predictive model may be judged solely on its predictive performance, although we will discuss why intelligibility is nonetheless important. The difference between these model types is not as strict as this may imply. Some of the same techniques can be used for both, and usually, one model can serve both purposes, though sometimes poorly. Sometimes, much of the value of a predictive model is in the understanding gained from looking at it, rather than in the predictions it makes. Before we discuss predictive modeling further, we must introduce some terminology. Supervised learning is model creation where the model describes a relationship between a set of selected variables, attributes or features, and a predefined variable called the target variable. The model estimates the value of the target variable as a function, possibly a probabilistic function, of the features. So, for our churn prediction problem, we would like to build a model of the propensity to churn as a function of customer account attributes, such as age, income, length with the company, number of calls to customer service, overage charges, customer demographics, data usage, and others. Now, let's consider the terminology used in a sample model for credit write-off prediction. We use the term instance or example to represent a fact or a data point. In this case, a historical customer who had been given credit. This is also called a row in database or spreadsheet terminology. Each instance is described by a set of attributes, fields, columns, variables, or features. In this example, the attributes for each customer are name, balance, age, employed, and write-off. The last two of which take yes/no values. Write-off is the target attribute, the one we're trying to predict. This credit write-off prediction example is known as a supervised classification problem. It is a supervised problem because it has a target attribute and some training data where we know the value for the target attribute, and it is a classification rather than a regression problem because the class label, the value of the target, is a category, yes or no, rather than a number. If we were trying to predict a number such as the predicted amount of the write-off, then it would be a regression. Note that an instance is also sometimes called a feature vector because it can be represented as a fixed-length, ordered collection, vector, of feature values. For example, our sample model might include the feature vector Claudio, name, 115,000, bank balance, 40, age, no, employment status. Many names for the same things. The principles and techniques of data science historically have been studied in several different fields, including machine learning, pattern recognition, statistics, databases, and others. As a result, there often are several different names for the same things. We typically will refer to a data set, whose form, usually is the same as a table of a database or a worksheet of a spreadsheet. A dataset contains a set of examples or instances. An instance also is referred to as a row of a database table, or sometimes a case in statistics. The features, table columns, have many different names as well. Statisticians speak of independent variables or predictors as the attributes supplied as input. In operations research, you may also hear explanatory variable. The target variable, whose values are to be predicted, is commonly called the dependent variable in statistics. This terminology may be somewhat confusing. The independent variables may not be independent of each other, or anything else. And the dependent variable doesn't always depend on all the independent variables. For this reason, we have avoided the dependent-independent terminology in this book. Some experts consider the target variable to be included in the set of features. Some do not. The important thing is rather obvious. The target variable is not used to predict itself. However, it may be that prior values for the target variable are quite helpful to predict future values. So such prior values may be included as features. The creation of models from data is known as model induction. Induction is a term from philosophy that refers to generalizing from specific cases to general rules, or laws or truths. Our models are general rules in a statistical sense. They usually do not hold 100% of the time, often not nearly. And the procedure that creates the model from the data is called the induction algorithm or learner. Most inductive procedures have variants that induce models both for classification and for regression. We will discuss mainly classification models because they tend to receive less attention in other treatments of statistics, and because they are relevant to many business problems, and thus, much work in data science focuses on classification. Note: induction can be contrasted with deduction. Deduction starts with general rules and specific facts and creates other specific facts from them. The use of our models can be considered a procedure of probabilistic deduction. We will get to this shortly. The input data for the induction algorithm, used for inducing the model, are called the training data. As mentioned in Chapter 2, they are called labeled data because the value for the target variable, the label, is known. Let's return to our example churn problem. Based on what we learned in Chapter 1 and Chapter 2, we might decide that in the modeling stage, we should build a supervised segmentation model, which divides the sample into segments having, on average, a higher or lower tendency to leave the company after contract expiration. To think about how this might be done, let's now turn to one of our fundamental concepts. How can we select one or more attributes, features, or variables that will best divide the sample with respect to our target variable of interest? Supervised segmentation. Recall that a predictive model focuses on estimating the value of some particular target variable of interest. An intuitive way of thinking about extracting patterns from data in a supervised manner is to try to segment the population into subgroups that have different values for the target variable, and within the subgroup, the instances have similar values for the target variable. If the segmentation is done using values of variables that will be known when the target is not, then these segments can be used to predict the value of the target variable. Moreover, the segmentation may at the same time provide a human understandable set of segmentation patterns. One such segment expressed in English might be: middle-aged professionals who reside in New York City on average have a churn rate of 5%. Specifically, the term middle-aged professionals who reside in New York City is the definition of the segment, which references some particular attributes, and a churn rate of 5% describes the predicted value of the target variable for the segment. Often, we are interested in applying data mining when we have many attributes, and are not sure exactly what the segments should be. In our churn prediction problem, who is to say what are the best segments for predicting the propensity to churn? If there exist in the data segments with significantly different average values for the target variable, we would like to be able to extract them automatically. This brings us to our fundamental concept. How can we judge whether a variable contains important information about the target variable? How much? We would like to automatically get a selection of the more informative variables with respect to the particular task at hand, namely, predicting the value of the target variable. Even better, we might like to rank the variables by how good they are at predicting the value of the target. Consider just the selection of the single most informative attribute. Solving this problem will introduce our first concrete data mining technique. Simple, but easily extendable to be very useful. In our example, what variable gives us the most information about the future churn rate of the population? Being a professional? Age? Place of residence? Income? Number of complaints to customer service? Amount of overage charges? We will now look carefully into one useful way to select informative variables, and then later, we will describe how this technique can be used repeatedly to build a supervised segmentation. While very useful and illustrative, please keep in mind that direct, multivariate supervised segmentation is just one application of this fundamental idea of selecting informative variables. This notion should become one of your conceptual tools when thinking about data science problems more generally. For example, as we go forward, we will delve into other modeling approaches, ones that do not incorporate variable selection directly. When the world presents you with a very large set of attributes, it may be extremely useful to harken back to this early idea and to select a subset of informative attributes. Doing so can substantially reduce the size of an unwieldy dataset, and, as we will learn, will often improve the accuracy of the resultant model. Selecting informative attributes. Given a large set of examples, how do we select an attribute to partition them in an informative way? Let's consider a binary, two-class, classification problem and think about what we would like to get out of it. In this example, we have 12 people represented as stick figures. There are two types of heads, square and circular, two types of bodies, rectangular and oval, and two of the people have gray bodies while the rest are white. Thus, the attributes we use to describe the people are head shape, square or circular, body shape, rectangular or oval, and body color, gray or white. Each person is also assigned a binary target label, yes or no, indicating, for example, whether the person becomes a lone write-off. This is the target variable. So, let's ask ourselves, which of the attributes would be best to segment these people into groups, in a way that will distinguish write-offs from non-write-offs? Technically, we would like the resulting groups to be as pure as possible. By pure, we mean homogeneous with respect to the target variable. If every member of a group has the same value for the target, then the group is pure. If there is at least one member of the group that has a different value for the target variable than the rest of the group, then the group is impure. Unfortunately, in real data, we seldom expect to find a variable that will make the segments pure. However, if we can reduce the impurity substantially, then we can learn something about the data and the corresponding population. Importantly for this chapter, we can also use the attribute in a predictive model. In our example, predicting that members of one segment will have higher or lower write-off rates than those in another segment. If we can do that, then we can, for example, offer credit to those with the lower predicted write-off rates, or offer different credit terms based on the different predicted write-off rates. Technically, there are several complications. Attributes rarely split a group perfectly. Even if one subgroup happens to be pure, the other may not be. For example, let's say one of our two gray body stick figures is a write-off and the other is not. If the gray body write-off weren't there, then the gray body color attribute would create a pure segment, no write-off. However, the other associated segment, white body color, includes people who are and aren't write-offs, meaning that segment is still not pure. In the prior example, the gray body color condition only splits off one single data point into the pure subset. Is this better than another split that does not produce any pure subset but reduces the impurity more broadly? Not all attributes are binary. Many attributes have 3 or more distinct values. We must take into account that one attribute can split into 2 groups, while another might split into 3 groups or 7. How do we compare these? Some attributes take on numeric values, continuous or integer. Does it make sense to make a segment for every numeric value? No. How should we think about creating supervised segmentations using numeric attributes? Fortunately, for classification problems, we can address all the issues by creating a formula that evaluates how well each attribute splits a set of examples into segments with respect to a chosen target variable. Such a formula is based on a purity measure. The most common splitting criterion is called information gain, and it is based on a purity measure called entropy. Both concepts were invented by one of the pioneers of information theory, Claude Shannon, in his seminal work in the field. Entropy is a measure of disorder that can be applied to a set, such as one of our individual segments. Consider that we have a set of properties of members of the set, and each member has one and only one of the properties. In supervised segmentation, the member properties will correspond to the values of the target variable. Disorder corresponds to how mixed, impure, the segment is with respect to these properties of interest. So, for example, a mixed-up segment with lots of write-offs and lots of non-write-offs would have high entropy. More technically, entropy is defined as the negative sum of the probability, relative percentage, of each property within a set, times the log of that probability. If we had just 2 properties, entropy would be equal to negative P1 times the log of P1 minus P2 times the log of P2. Since the entropy equation might not lend itself to intuitive understanding, consider the following scenario. We have a set of 10 symbols, and each symbol is either a plus sign or a minus sign. If all 10 symbols are plus signs, then entropy is 0. There is no disorder because we have full uniformity. If all 10 symbols are minus signs, then, by the same reasoning, entropy is still 0. Entropy will be maximized, having a value of 1, when the instance classes are balanced, or when we have 5 of each symbol. Put simply, entropy measures the general disorder of a set, ranging from 0, at minimum disorder, in which all of the set's members have the same single property, to 1, at maximal disorder, in which the properties of the set's members are equally mixed. But entropy is only part of the story. We would like to measure how informative an attribute is with respect to our target, how much gain in information it gives us about the value of the target variable. An attribute segments a set of instances into several subsets. Entropy only tells us how impure one individual subset is. Fortunately, with entropy to measure how disordered any set is, we can define information gain, IG, to measure how much an attribute improves, decreases, entropy over the whole segmentation it creates. Strictly speaking, information gain measures the change in entropy due to any amount of new information being added. Here, in the context of supervised segmentation, we consider the information gained by splitting the set on all values of a single attribute. Let's say the attribute we split on has k different values. Let's call the original set of examples the parent set, and the result of splitting on the attribute values the k children sets. Thus, information gain is a function of both a parent set and of the children resulting from some partitioning of the parent set. How much information has this attribute provided? That depends on how much purer the children are than the parent. Stated in the context of predictive modeling, if we were to know the value of this attribute, how much would it increase our knowledge of the value of the target variable? Specifically, information gain can be defined as the entropy of the parent minus the entropy of each child, multiplied by the proportion of instances belonging to that child. So, if we had 2 children, information gain would equal the entropy of the parent minus the entropy of child 1 times the proportion of instances belonging to child 1 minus the entropy of child 2 times the proportion of instances belonging to child 2. Note that weighting each child by the proportion of instances belonging to that child directly addresses our concern that splitting off a single example and noticing that the set is pure may not be as good as splitting the parent set into 2 nice, large, relatively pure subsets, even if neither is entirely pure. As an example, let's go back to our credit write-off scenario, in which we attempt to figure out which customers are likely to default. Again, this problem has 2 classes, good customers and bad customers. Let's also say we have 2 child sets, one showing write-off results for customers with a bank balance of less than $50,000, and one showing write-off results for customers with a bank balance of greater than $50,000. The parent set has 30 instances consisting of 16 good customers and 14 bad ones, or a near even split, meaning it's very impure and has an entropy value close to 1. The entropy of each of the child sets, on the other hand, is lower. The set of customers with a bank balance below $50,000 shows 1 good customer and 12 write-offs, whereas the set of customers with a bank balance above $50,000 shows 13 good customers and 4 write-offs. This seems to indicate a pattern. Customers with lower bank balances are more likely to default, while customers with high bank balances are less likely to do so. If we were to calculate the information gain, we'd find that splitting our initial parent set into these 2 child sets reduces entropy substantially. In predictive modeling terms, the attribute provides a lot of information on the value of the target. Thinking back on our concerns about creating supervised segmentation for classification problems, information gain addresses them all. It does not require absolute purity, it can be applied to any number of child subsets, and it takes into account the relative sizes of the children, giving more weight to larger subsets. Numeric variables. We have not discussed what exactly to do if the attribute is numeric. Numeric variables can be discretized by choosing a split point, or many split points, and then treating the result as a categorical attribute. For example, income could be divided into 2 or more ranges. Information gain can be applied to evaluate the segmentation created by this discretization of the numeric attribute. We still are left with the question of how to choose the split point, or points, for the numeric attribute. Conceptually, we can try all reasonable split points and choose the one that gives the highest information gain. Finally, what about supervised segmentations for regression problems, problems with a numeric target variable? Looking at reducing the impurity of the child subsets still makes intuitive sense, but information gain is not the right measure, because entropy-based information gain is based on the distribution of the properties in the segmentation. Instead, we would want a measure of the purity of the numeric target values in the subsets. We will not go through a derivation here, but the fundamental idea is important. A natural measure of impurity for numeric values is variance. If the set has all the same values for the numeric target variable, then the set is pure and the variance is 0. If the numeric target values in the set are very different, then the set will have high variance. We can create a similar notion to information gain by looking at reductions in variance between parent and children. To create the best segmentation, given a numeric target, we might choose the one that produces the best weighted average variance reduction. In essence, we again would be finding variables that have the best correlation with the target, or alternatively, are most predictive of the target. Example: attribute selection with information gain. now we are ready to apply our first concrete data mining technique. For a dataset with instances described by attributes and a target variable, we can determine which attribute is the most informative with respect to estimating the value of the target variable. We can also rank a set of attributes by their informativeness, in particular, by their information gain. This can be used simply to understand the data better. It can be used to help predict the target. Or it can be used to reduce the size of the data to be analyzed by selecting a subset of attributes in cases where we cannot or do not want to process the entire dataset. To demonstrate the use of information gain, we introduce a simple but realistic dataset taken from the Machine Learning Dataset Repository at the University of California at Irvine. It is a dataset describing edible and poisonous mushrooms taken from the Audubon Society Field Guide to North American Mushrooms. From the description, this dataset includes descriptions of hypothetical samples corresponding to 23 species of gilled mushrooms in the Agaricus and Lepiota family. Each species is identified as definitely edible, definitely poisonous, or of unknown edibility and not recommended. This latter class was combined with the poisonous one. The guide clearly states that there is no simple rule for determining the edibility of a mushroom, no rule like leaflets 3 let it be for poisonous oak and ivy. Each data example or instance is one mushroom sample, described in terms of its observable attributes, its features. The 20-odd attributes for each example include cap shape, with values like flat and conical, cap color, with values like brown and white, odor, with values like almond and fishy, whether it's bruised, with the values yes and no, and so on. For a given example, each attribute takes on a single discrete value. For example, gill color equals black. We use 5,644 examples from the dataset, comprising 2,156 poisonous and 3,488 edible mushrooms. This is a classification problem because we have a target variable called edible, with two values, yes, meaning the mushroom is edible, and no, meaning the mushroom is poisonous, specifying our two classes. Each of the attributes in the training set has a value for this target variable. We will use information gain to answer the question, which single attribute is the most useful for distinguishing edible mushrooms from poisonous ones? This is a basic attribute selection problem. In much larger problems, we could imagine selecting the best 10 or 50 attributes out of several hundred or thousand. And often, you want to do this if you suspect there are far too many attributes for your mining problem, or that many are not useful. Here, for simplicity, we will find the single best attribute instead of the top 10. Since we now have a way to measure information gain, this is straightforward. We are asking for the single attribute that gives the highest information gain. To do this, we calculate the information gain achieved by splitting on each attribute. The information gain is defined on a parent and a set of children. The parent in this case is the whole dataset. So first, we need the entropy of the dataset. If the two classes were perfectly balanced in the dataset, it would have an entropy of 1. This dataset is slightly unbalanced. More edible than poisonous mushrooms are represented, so its entropy is 0.96. To explain entropy reduction graphically, we'll walk through a number of entropy graphs for the mushroom domain. Each graph is a two-dimensional description of the entire dataset's entropy as it is divided in various ways by different attributes. On the x-axis is the proportion of the dataset, from 0 to 1, and on the y-axis is the entropy, also from 0 to 1, of a given piece of the data. The amount of shaded area in each graph represents the amount of entropy in the dataset when it is divided by some chosen attribute. Our goal of having the lowest entropy corresponds to having as little shaded area as possible. The first graph shows the entropy of the entire dataset. In such a graph, the highest possible entropy corresponds to the entire area being shaded. The lowest possible entropy corresponds to the entire area being white. This graph is useful for visualizing information gain from different partitions of a dataset, because any partition can be shown simply as slices of the graph, with widths corresponding to the proportion of the dataset, each with its own entropy. The weighted sum of entropies in the information gain calculation will be depicted simply by the total amount of shaded area. For our entire dataset, the global entropy is 0.96. So, this first chart has a horizontal line at y equals 0.96, with a large shaded area below it. We can think of this as our starting entropy. Any informative attribute should produce a new graph with a smaller shaded area. Now, we discuss the entropy charts of 3 sample attributes. Each value of an attribute occurs in the dataset with a different frequency, so each attribute splits the set in a different way. If we split the dataset with the attribute gill color, whose values indicate yellow, purple, and so on, our new chart includes a bar for each color. The width of each bar represents what proportion of the dataset has that gill color, and the height of each bar represents its entropy. Splitting the dataset by gill color reduces the entropy somewhat. The shaded area is now considerably smaller than the area in our first chart. For example, the entropy for the color brown, which makes up over 20% of our dataset, is around 0.5. Similarly, splitting the dataset with the attribute spore print color also decreases uncertainty, or entropy. A few of the values, such as the color chocolate, specify the target value perfectly and thus produce 0 entropy bars. But they don't account for all that much of the population, only about 30%. Finally, splitting the dataset by odor results in the highest information gain of any attribute in the mushroom dataset. It reduces the dataset's total entropy to about 0.1, which gives us an information gain of 0.86. What is this saying? Many odors are completely characteristic of poisonous or edible mushrooms. So odor is a very informative attribute to check when considering mushroom edibility. If you're going to build a model to determine the mushroom edibility using only a single feature, you should choose its odor. If you are going to build a more complex model, you might start with the attribute odor before considering adding others. In fact, this is exactly the topic of the next section. Supervised segmentation with tree-structured models. We have now introduced one of the fundamental ideas of data mining: finding informative attributes from the data. Let's continue on the topic of creating a supervised segmentation, because as important as it is, attribute selection alone does not seem to be sufficient. If we select the single variable that gives the most information gain, we create a very simple segmentation. If we select multiple attributes, each giving some information gain, it's not clear how to put them together. Recall from earlier that we would like to create segments that use multiple attributes, such as middle-aged professionals who reside in New York City have an average churn rate of 5%. We now introduce an elegant application of the ideas we've developed for selecting important attributes to produce a multivariate, multiple attribute, supervised segmentation. Picture an upside-down tree made of nodes, with the root node at the top branching out into interior or terminal nodes as the tree expands downward. Each interior node contains a test of an attribute, with each branch from the node representing a distinct value or range of values of the attribute. Following the branches from the root node down, each path eventually terminates at a terminal or leaf node. Using our credit card write-off scenario as an example, let's create a classification tree starting with the root node employed. This node has 2 branches, yes and no. The yes branch leads to a leaf node that puts all employed customers in the not write-off class, while the no branch leads to an interior node that asks another question about the customer. Let's say that a particular customer is unemployed, so now we want to know a little more about them. We move down to the next node and ask about their bank balance. Like our root node, the balance node has two branches, over $50,000 and under $50,000. If a customer's bank balance is over $50,000, we can consider that customer not a write-off. But if the balance is under $50,000, we move down to the next interior node and ask another question, perhaps about the customer's age. Eventually, we will have answered enough questions to classify the customer as either a write-off or not a write-off. Trees such as this one create a segmentation of the data. Every data point will correspond to one and only one path in the tree, and thereby to one and only one leaf node. In other words, each leaf corresponds to a segment, and the attributes and values along the path give the characteristics of the segment. So, in our specific tree, the write-off path might correspond to the segment unemployed people with low balances. The tree is a supervised segmentation because each leaf contains a value for the target variable. Since we are talking about classification here, each leaf contains a classification for its segment. Such a tree is called a classification tree, or more loosely, a decision tree. Classification trees often are used as predictive models, tree-structured models. In use, when presented with an example for which we do not know its classification, we can predict its classification by finding the corresponding segment and using the class value at the leaf. Mechanically, one would start at the root node and descend through the interior nodes, choosing branches based on the specific attribute values in the example. The non-leaf nodes are often referred to as decision nodes, because when descending through the tree, at each node, one uses the values of the attribute to make a decision about which branch to follow. Following these branches ultimately leads to a final decision about what class to predict. Eventually, a terminal node is reached, which gives a class prediction. In a tree, no two parents share descendants, and there are no cycles. The branches always point downwards, so that every example always ends up at a leaf node with some specific class determination. Classification trees are one sort of tree-structured model. As we will learn later, in business applications, often we want to predict the probability of membership in the class, for example, the probability of churn or the probability of write-off, rather than the class itself. In this case, the leaves of the probability estimation tree would contain these probabilities rather than a symbol value. If the target variable is numeric, the leaves of the regression tree contain numeric values. However, the basic idea is the same for all. Trees provide a model that can represent exactly the sort of supervised segmentation we often want, and we know how to use such a model to predict values for new cases in use. However, we still have not addressed how to create such a model from the data. We turn to that now. There are many techniques to induce a supervised segmentation from a dataset. One of the most popular is to create a tree-structured model, tree induction. These techniques are popular because tree models are easy to understand and because the induction procedures are elegant, simple to describe, and easy to use. They are robust to many common data problems and are relatively efficient. Most data mining packages include some type of tree induction technique. How do we create a classification tree from data? Combining the ideas introduced earlier, the goal of the tree is to provide a supervised segmentation. More specifically, to partition the instances based on their attributes into subgroups that have similar values for their target variables. We would like for each leaf segment to contain instances that tend to belong to the same class. To illustrate the process of classification tree induction, consider the very simple example set of 12 people we introduced earlier, with either rectangular or round heads, rectangular or round bodies, and gray or white bodies. Tree induction takes a divide and conquer approach, starting with the whole dataset and applying variable selection to try to create the purest subgroups possible using the attributes. In the example, one way is to separate people based on their body type, rectangular versus oval. How good is this partitioning? Let's say that the rectangular body people are 5 write-offs, with a single non-write-off, so it is mostly pure. The